Okay, next section, we're going to be talking about infinite limits now. And yeah, so we're going to start with this example. We have a function, f of x. It's just x plus 2 divided by x plus 2 all over x squared minus 6x plus 9. And we want to find the limit as x is approaching 3. So, how do we do that? Well, remember, first thing you could do as a first attempt is, can we plug in 3? Right? Is this function continuous at 3? So, if we try plugging in 3, we get 3 plus 2 over 3 squared minus 6 times 3 plus 9. After all, if this function is continuous at 3, then that guarantees that this will be the answer. So the numerator is 5. The denominator is 9 minus 18 plus 9, which is 0. Okay, so that doesn't work. 5 divided by 0 is not a number. It's undefined. So that's not the limit. All right, so we can't do it that way. So what can we do then? Well, now we have to go back and we have to resort to using either a table or a graph. So let's do it numerically. Let's make a table. And again, just to stick with the book, I'm going to do this horizontally here and plug in numbers that are close to 3. So to the right of 3, that might be let's start way over here, 3.1, 3.01. Boy, I didn't need this much space, did I? Well, okay, so we'll do a lot of values here, right? So this will be 3.001, 3.01, 3.1, right? How's that? Okay. And when you're less than 3, you have 2.9, 2.99, and then 2.999. And if you need, you can add more 9s, you can add more 0s if you want. You'll see in this case it's probably not necessary. Okay, so just plug these in your calculator, right? And I'll show you what you get when you plug in 2.9, for example. You do all this. Plus 9. And you get, oh, it's not approximate. It's exactly 490, I think. 490, right? All right, you do this with 2.99, and you get 49,900. You do it with 2.999, and you get, let's see, 4,999,000. Pretty big number, right? When you plug in 3.1, you get 510. When you plug in 3.01, you get 51,100. When you plug in 3.001, you get 5,111,000. Again, a very big number, right? So remember, for the limit, we don't care what happens when x equals 3. In fact, we tried plugging in 3, and we said it was, undefined. I squeeze that in here. This is undefined at 3. But remember, we don't care about that. When we're finding the limit, all we care about is what happens when we approach 3, when we get close to 3. And so when we get close to 3, what numbers are these getting close to? You could say, well, 5 million, but that's only because we only did 3.001. Right? Trust me, if you plug in 3.0001, you're nowhere near 5 million anymore. Well, I think you're at 511,110,000. Okay, something like that, right? You're at 500 million. And if you plug in 3.00001, you're going to be at like 50 billion, right? So it's going to be like 5.1 times 10 to the 10th power. So you're getting really, really big. right? And the same thing happens on the right. These numbers are just getting bigger and bigger and bigger as well. So I think based on that, we can say that this limit does not exist. These numbers don't get close to anything. They just get bigger and bigger and bigger. Right. On the other hand, right, we could also say that this limit, as x approaches 3, again, same function. And in fact, we can see what goes wrong here. If we factor the denominator, we actually just get x minus 3 squared. Okay, so the denominator gets smaller. It's getting closer to 0. The numerator is getting, well, it's not getting bigger. It's getting closer to 5. But it doesn't matter, right? If the numerator is 5 and the denominator gets smaller and smaller and smaller, the whole thing just gets bigger. So it approaches infinity. And again, remember, infinity is not a number. So these two statements are not inconsistent here. The limit does not exist specifically because the y values just blow up. They get bigger and bigger and bigger. Okay? So this is just a more specific way, more specific statement, a more precise statement that the limit is approaching infinity. Right? But that's because the limit does not exist. It's not a number. Right? So that's what we mean by an infinite limit. Okay? On the other hand, let's look at this example. I'll call it g of x this time. Right? Suppose this is just negative 1 over x to the 4th. Okay, and we want to find or evaluate the following limit. Limit as x approaches 0 of g of x. What is that limit? So this is the limit x is approaching 0 of negative 1 over x to the 4th. So again, you cannot plug in 0 because you just get, well, negative 1 over 0, which is undefined. But that has nothing to do with the limit, right? You can plug in numbers close to 0, like 0.0001 or something like that, or negative 0.001. You got to do both sides, left and right, positive and negative. But we did that in the last example. In this example, I'd rather just make a graph. And the graph will look something like this. Okay, so here's x equals 0. It's just the y-axis. Well, the y values seem to be getting bigger, but this time in the negative direction. Right? Remember, going up is positive. That would be going to positive infinity. If you're going down, that's to negative infinity. So, yep, the answer here would be negative infinity. But again, the limit does not exist. It's not a specific number. Okay, this negative infinity just means that, right, the y values get bigger and bigger and bigger, but in the negative direction. Okay, let's do another example. Suppose I'll go back to f of x, I guess. F of x is 1 over x minus 2. And we want to evaluate the limit as x approaches 2. So what is that limit? So again, don't try plugging in 2 here. It's not going to work. 2 minus 2 is 0, and 1 over 0 is not a number. So that does not work, right? So what can we do? We can make a table, or, as we did last time, just draw the graph. And you'll see what happens here. You have another vertical asymptote. Yep. This time at x equals 2. So what's happening if you're approaching 2 from the right side, the y values just get bigger. They go to positive infinity. But from the left side, it seems like they're going to negative infinity. So what does that mean for the limit here? Well, it means the limit does not exist. We have to leave it at that, right? You might be tempted to say, well, it's plus or minus infinity. But you can't do that. That doesn't make any sense, right? Any more than you can say that the limit is plus or minus 4. Well, which is it? Is it positive 4 or is it negative 4? Because it can't be both, right? The limit cannot be two different numbers. Likewise, it cannot be two different infinities. It cannot be a positive infinity. It cannot be a negative infinity, right? When you plug in a number close to 2, but bigger than 2, you get a very big number. I think something like 1,000, right? Yeah, I think so. But when you plug in a number less than 2, right, then you get negative 1,000, which is big, but it's negative, right? So on the right side, you're going to positive infinity. On the left side, you're going to negative infinity. So you don't say the limit is infinity. You don't say it's negative infinity. You give up, and you just say it does not exist. Okay? All right, good. Yeah. So, so what we could do, of course, is the following. We can say that the limit, as x approaches 2 from the left of this function, from the left, that's going to be negative infinity. And then from the right, as x approaches 2 from the right, we can say that's positive infinity. Okay, so again, we're talking about left-handed and right-handed limits. But here, in the original question, there was no plus, right? There was no minus. So this means from both sides, from right and left. And unless they're the same number or the same infinity, both positive or both negative, right? In example 2, they were both negative. In example 1, they were both positive, right? So you can say positive infinity here, right? You can say negative infinity here. Right? But in this example, one side goes up, one side goes down. You give up. You don't say it's positive infinity or negative infinity. The limit does not exist. But you can do the left-handed limit and the right-handed limit separately. And again, you get two different answers. One's negative, one's positive, right? So I hope that helps. Okay. In fact, we can use this idea of infinite limits to define a vertical asymptote. Now, in your pre-calc days, you might say, well, they did that in pre-calculus, right? They told us what a vertical asymptote is. And they really didn't. We really never defined what a vertical asymptote is, other than to say that, well, it's a line, it's a vertical line, right? Something like this, that the graph approaches, right? The graph approaches that line. So something like this, or this. So we know it when we see it, right? We know that this line here is a vertical asymptote. But we didn't specifically define it, at least not formally, not rigorously, because in order to define it, we need the idea of a limit. Right? So the line x equals c, being a vertical line, is a vertical asymptote if either, I should say here, if either one of these limits is true. Okay? So either the limit as x approaches c from the left of the function is positive infinity, or it could be negative infinity. Right? Or if you're coming from the right side and you get infinity or negative infinity, you get a vertical asymptote. Right? So this you can think of as the actual definition of a vertical asymptote. And specifically, when we gave you the natural log function, remember natural log of x? We told you that you have a vertical asymptote. I shouldn't use yellow here. We told you that this graph has a vertical asymptote. But we really never said why, right? So here's 1, 2, 3. Right, so the graph of natural log, if you remember, looks like this. Right. And it just keeps going down, and it approaches the line x equals 0. Right? So for the natural log function, x equals 0 is a vertical asymptote. And now we can see why. If we take the limit as x approaches 0, but only from the right side, right? There's nothing on the left here. So we have to approach 0 from the right. And this is the natural log function. Well, we're not going up, right? We're going down to negative infinity. Right? So this limit is negative infinity here. Right? Which means the limit does not exist, but specifically because it just gets more and more negative as the further down you go. Right, so call that up, right? Right. So yeah, specifically here we're using this plus and this minus, but that's one of the 4 possibilities for a vertical asymptote, right? So the point is, right, it doesn't have to approach from both sides, left and right. It could just be a one-sided limit, right, or one-sided asymptote, as it is for the natural log function. Okay. Yeah, so let's do an example that you probably have done before. So find the vertical asymptote of the function. So let's do x plus 5 over x squared plus 6x plus 5. Okay. Yeah, this you did this in pre-calc. So it's a good review. And what did you do? Well, remember in pre-calc, to find a vertical asymptote, right, you set the denominator equal to 0 and solve for x. So here the denominator is x squared plus 6x plus 5. You just solve this little quadratic equation. You can use the quadratic formula if you like. I'm just going to factor it. This is x plus 1, times x plus 5. So you get 2 solutions. You get x equals -1 and x equals -5. So what does that mean? Does that mean we have 2 vertical asymptotes? Well, no. Remember, even in pre-calc, you had to simplify this first. Right. X plus 5 is also a factor of the numerator. So they cancel. So when you simplify, you just get 1 over x plus 1. Right. So specifically, that's what you should be setting equal to 0. And that gives you your vertical asymptote. There's only one. Okay, so x equals -1 is the vertical asymptote. And that's it. Okay, what about x equals -5? Where did that come from? Well, that came from setting the denominator 0, but notice the numerator is also 0. So if x is -5, right, and you try plugging it in, you get 0 over 0. And if you remember, that's a good indication that you just have a hole in the graph. So at x equals -5, this is not a vertical asymptote. It's just a hole in the graph. But at -1, that's where you have your vertical asymptote. So 2 points of discontinuity, right? The negative 5 is a discontinuity, but it's removable because it's a whole. But at negative 1, it's a vertical asymptote, and remember, that's non-removable. Just to remind you of that. Right. Yep. So it's not setting the denominator equal to 0. It's setting the denominator equal to 0 after you simplify. Sorry, a little sloppy here. So you set the denominator equal to 0 after you simplify, right? After you factor and cancel. So yeah, we had to do this first. This is the simplified version. And then we set that denominator equal to 0. That gives you your vertical asymptote. Okay. If the numerator and denominator are both 0, right, that gives you the hole in the graph. Right. So, okay. Anyways, so that's a good a review example. You did this in pre-calc. But let's make this official. And I'll bring up a property here. Okay, so rather than write it down, I just copied it out of my notes. And in fact, I just copied it out of the book. So this is Theorem 114. We have two continuous functions, f and g, on a neighborhood of c. And that just means you're close to c. Right? If f of c is not 0, I should be clear on that, right? So if f of c is not 0 and g of c is equal to 0, and g of x is not 0 near c, right, then h of x, so I need to go back to this. So h of x is our rational function, right? We have a numerator and denominator. The numerator is f. The denominator is g. Okay? So what we're saying here, right, is if the denominator is 0, yeah, right? So if g of x equals 0, but f of x is not equal to 0, right, then you have a vertical asymptote at x. Well, specifically at c here. Sorry, so this should be a c. There should be a c. So if g of c equals 0 and f of c is not 0, then you have a vertical asymptote of x equals c. Okay? So, yeah, this just makes it official. What you did in pre-calc, right? If the denominator is 0, but not the numerator, then you have a vertical asymptote. Right? If they're both equal to 0, and maybe that's not part of the theorem, of course, but, right, if g of c equals 0 and f of c equals 0, then you probably have a hole at x equals c. But again, that's not the whole story. You have to check left and right. You have to check in the neighborhood of c that these are not equal to 0 in a neighborhood of c. But basically, right, when you get 0 over 0, chances are that's a hole, right? If you get something like, 15 divided by 0, that's probably a vertical asymptote. Vertical asymptote, right? So that's all this theorem says, right? It's exactly what you have been using in your pre-calc days. Now we just made this formal statement, and that allows us to do what you did in pre-calc. Find the vertical asymptotes by figuring out where the denominator is 0, but where the numerator is not 0. Okay. Right, and then one last property for this section, and I think for the chapter as well. This is all chapter 1. So we're letting C and L be real numbers. Right, so C and L are real numbers. So this little boldface R here, it just means real numbers. That's my fancy way to write real numbers. Again, this is my notes. I would write this out in class. And we are given, in fact, let me write it down over here, right? The limit as x approaches c of f of x is positive infinity. And the limit as x approaches c of g of x exists and is some number L. Okay, right? So these are given. We know these, right? So the first statement here just says that if I add f of x plus g of x or subtract f of x plus g of x, that limit also has to be infinity. Okay? So yeah, the first statement, we're taking the limit as x approaches c of f of x plus g of x, then that also has to be infinity. Or if we take f of x minus g of x, again, we still get infinity. Okay. So yeah, here's a good example of that. Suppose you want to find the limit as x approaches, x approaches 1 of 3x plus 4 plus 2 over x minus 1 squared. Okay. And so we're adding two functions. I'm going to consider this to be my g of x. So I kind of have it backwards here. And this will be my f of x. So it's g of x plus f of x, but that's the same as f of x plus g of x. Right. So you remember, of course, that you can split this up as two separate limits here. We can take the limit of just 3x plus 4, and then to add to that, take the limit of 2 over x minus 1 squared. So this limit we can calculate very easily because it's a continuous function, right? It's a linear function. You know straight lines are continuous, right? So we plug in 1 here. 3 plus 4 is 7. But what's this limit, right? So notice the numerator is just a number. The denominator gets smaller and smaller and smaller, right? Right, as x approaches 1, this approaches 0. So the fraction just gets bigger and bigger and bigger. The fraction goes to infinity. So what's 7 plus infinity? Well, look, infinity is already like really, really big. Adding 7 to infinity doesn't really change the fact that it's a big number. So of course you still get infinity as this says, right? So yeah. Basically, adding anything to infinity still gives you infinity. Right? Or even subtracting, right? If this were a minus 7, right? So you're taking away a little bit from infinity, but it's still infinity, right? So that's the idea of this first statement here. The second one is a little more complicated, right? So it's you're multiplying f of x times g of x. So let me write that down over here. So we're taking the limit as x approaches c of f of x times g of x. And that's going to depend on L. That's going to depend on the limit of g of x. So you're going to get positive infinity if L is positive, and you're going to get negative infinity if L is negative. I think that's what we have here. Yep. Right. So yeah, here you have to be careful. Here you probably can't split these up in most cases. Okay, so it's kind of hard to find a good example of this, but I think I can come up with one. So how about the limit as x approaches 0 of 1 over x cubed. Nope, can't be x cubed, right? It has to be x to the 4th times 3x plus 2 over 1. Okay, so I think this will work, right? This is my f of x here, and this is my g of x. So I'm just multiplying two functions, right? Of course, you could think of this as just 3x plus 2 all over x to the 4th. And in fact, if you see that, you probably want to split this up like this. Okay. So what's the limit of g of x? As x approaches 0, 3x plus 2 just approaches 2, right? 3 times 0 plus 2. So that's my L, right? And L, notice, is positive here. And notice that for f of x, the limit as x approaches 0 of f of x is, again, infinity. Right? So this is infinity times 2, which is infinity. Right? So that's it. So just using this property here, as long as your L is positive, then that's fine. Right. What would have happened if I can do this down here? Right. So very similar example. X is still going to 0. And I still have 1 over x to the 4th. But now it's going to be times 3x minus 2 over 1. Right. So what's that going to be? So in this case, again, the f of x still goes to infinity, but now, as x approaches 0 of 3x minus 2, that limit will be negative 2. Okay? So in this case, we're going to get negative infinity. Right? Think of it this way, right? It's infinity times negative 2. Right? It's a positive times a negative, so that makes it negative infinity. And you really shouldn't think of it like this, but in this case, it doesn't hurt to do it that way. Right? So that's the second property here. And then there's one more, this third one. The limit as x approaches c of g of x over f of x, that should equal 0. Okay, so let's look at an example of that. Let's write it down again so we don't forget. X approaches c, this was g of x divided by f of x, that this limit is 0. Okay. And again, kind of hard to come up with an example of this, but I'll do my best. Okay, so let's say we want to find the limit as x approaches 0. Let's do x minus 3 over 1 over x squared. Now, so I know that's a little awkward, but it illustrates the point here. The numerator approaches negative 3, which is negative, but it's finite. The denominator, right, approaches infinity. Right? So the whole thing then should approach 0. And there's a much easier way to see that. Right? If you're dividing by 1 over x squared, you're really multiplying by x squared. Right? So by simplifying this, you just get x cubed minus 3x squared. And as x is approaching 0, you just get 0 minus 0, which is 0. Right? But in this form here, we can see that this approaches some finite number L, which in this case is negative 3, but this approaches infinity. Right? This limit does not exist in the denominator. Right? It just gets bigger and bigger and bigger. So when the denominator gets bigger, the whole fraction gets smaller. It approaches 0. Okay. So yeah, that's one example. If you want another one that's maybe not quite as contrived, we can do this. How about the limit as x approaches pi over 2 from the left of, let's do 3x over cosecant x. Right, so what would that be? Right, so here my numerator approaches some finite number, right? This will be 3 pi over 2. Right, so that's my L. Right, so what's the denominator doing here? What's, right, cosecant of pi over 2? Well, it's undefined, right? It's undefined. But we can take the limit as x approaches pi over 2 from the left. And the easiest way to do that is recognize that cosecant is, by definition, 1 over the sine. Right? And you remember sine of pi over 2 is, hang on, sine of pi over 2 is 1. Oh, darn. Okay, so I think I messed this up. Hang on. Yeah, okay, sorry about this. I didn't mean pi over 2, I just meant pi. So erase the over 2, right? Yeah, cosecant of pi over 2 is not undefined, it's 1. Yeah. Okay, so we're approaching pi from the left, not pi over 2. So we're still approaching from the left, right? But yeah, this is going to be, erase this here. Right. Cosecant of pi is undefined. Right. Sine of pi is 0. Right. So this is like 1 over 0, which of course is undefined. But in the limit, right, if this is the sine function, and we're approaching pi from the left side, right, then it's approaching 0 from the positive side, right? So this should be positive infinity. Right? So again, the denominator, right, is going to positive infinity. So the whole thing gets smaller. It goes to 0. Okay. So yeah, I didn't mean pi over 2, I meant pi. Again, if you see me doing anything funny or anything that doesn't look right, you can always send me an email. Because, yeah, I make mistakes too. It happens all the time. Sorry about that. But anyways, that should be an example for each of these properties up here. And, yeah, I mean, it should make sense, right? Essentially, if you take infinity plus or minus any number, you still get infinity, right? If you take infinity times a positive number, you still get infinity. If you take infinity times a negative number, then you get negative infinity, right? So infinity times a negative number gives you negative infinity. And then anything divided by infinity, right? 7 divided by infinity effectively is just 0, right? It approaches 0. So that's the idea for all three of these. Again, you do have to be careful because in some examples it's not always clear. So for example, what's the limit as x approaches, let's say 0, of 1 over x squared minus 1 over x to the 4th? Okay, well, on the one hand, you might think, well, 1 over x squared, if the denominator gets smaller, this blows up, right? This goes to infinity. But so does this. This blows up too, so this goes to infinity. And then you might think, well, infinity minus infinity has to be 0. Well, not necessarily, right? Not necessarily. Infinity minus infinity is indeterminate. It could be anything. Right? So how can we calculate this limit? Is it really 0? Right? Is it really 0? Well, in this case, I think it is. So let's simplify this, right? If we get a common denominator, this just becomes x squared minus 1, right, all over x to the 4th. And yep, as the denominator, right, so the numerator gets close to -1, the denominator gets close to 0, Yeah, so let's see. We have this, the numerator approaches -1, which is your L. The denominator approaches infinity. We're in this case, right? So yeah, I think in case 3, we do get 0 here. Right, I think we do get 0. Hang on, that doesn't seem right to me. No, I got it backwards. The denominator gets smaller, so the whole thing gets bigger. This is infinity here. This goes to infinity. Okay. So in this case, yeah, infinity minus infinity is infinity, not 0. Okay. So yeah, you have to be careful about that, right? Infinity minus infinity is indeterminate. It could be 0. It could be infinity. It could be any number. It could be any number. And just to show that, I'll do one last example, and then we'll end it with that. Okay, so yeah, limit as x goes to 0 of 3 over x squared minus 2 over x squared. Right. So notice that 3 over x squared, as x goes to 0, this just gets bigger, so this goes to infinity. This goes to infinity. So it looks like infinity minus infinity. Right. But in this case, we really do get 0 here. And the easiest way to see that is simplify again. Right? This is just 3 minus 2 all over x squared, common denominator. So we're just taking the limit as x goes to 0 of 1 over x squared. Right. But as the denominator... Oh, no, I'm sorry. We don't get 0 again. We get infinity. Right? This is still infinity. Oops. Okay. Fair enough. Like I say, infinity minus infinity could be anything. Could be infinity. Could be 0. You know what? You can probably figure out where you do get 0. Very easy. Just do this. How's that, right? So individually, of course, this is still infinity minus infinity. But before you think of it that way, when you simplify, you're just subtracting itself, right? 3 minus 3 is 0. So take the limit as x approaches 0 of 0. That's where you get 0. That's where you get 0. So, yeah. So infinity minus infinity. Could be 0, could be infinity. And if you're clever, you can get it to be any number you want, right? So you can have infinity minus infinity equals 12. But in any event, we don't need to get any further into that. Right. So your indeterminate forms, just to mention, indeterminate, right? We already saw 0 divided by 0 is indeterminate. Now we have another one, infinity minus infinity is indeterminate. Also, infinity divided by infinity is indeterminate. Okay? So, and I think there's maybe a couple others, but this is good enough for now. For the most part, 0 divided by 0 is the one you're going to see the most often. When you get to calculus 2, however, you'll see these more often, I think, fairly often. But for now, that's all you need. I hope this helps.